So we'll continue our review with section 14.5, looking at improper integrals. Remember, the method is to, first of all, these are integrals that have infinity as one of their limits of integration. And we go about doing this by replacing that infinity with a letter m, thinking of it ending at some point. And then after we do the integration, we let that limit of that value go to infinity. If the part that has the infinity part, the m part in it, if it converges, which means that basically it will go to some value, usually 0, but it could be another value. It goes to some value. It means it's effectively it ends at some sort of finite level. Then we're able to actually get the limit. If it diverges, which means it goes off to infinity, we're done. It's a divergent integration because it doesn't have a limit. Okay, so let's take a look at this first one here. And what we're going to do is we're going to rewrite this as the integral going from 1 to m, because that's the infinity part. We're going to put this limit out here, and that's what makes it all okay. We're going to let m go to infinity, take the limit as it goes to infinity. We're going to rewrite this of 8 over x squared to be 8x to the minus 2 dx. Okay. Now we can readily integrate this. This becomes, we add 1 to the exponent, remember? So we're going to, as we integrate this, we get 8x to the minus 1, negative 2 plus 1. And then we divide by this new exponent. And since we're thinking of this as a definite integral, the limits of integration go from 1 to m. Using the fundamental theorem of calculus, what we do is we plug in these limits. So we're going to rewrite this just as negative 8x to the minus 1. And actually, I'm going to rewrite it with the x in the denominator. Okay, so now let's go ahead and do that. So we'll rewrite this as minus 8 over x, going from 1 to m. So now let's plug in. We first plug in the m, so we get minus 8 over m. Notice I put the m in for x. Subtract, the second part is when we plug in 1 for x. So put a parentheses, we get negative 8 over 1. And again, I just plug the 1 in for x. Now let's see what happens. So, and again, in doing all of this, we still have our limit coming down. Okay, it would have been over there. So now we take the limit. Oops. That's a terrible limit. Let's make it a little nicer. It looks more like a logarithm, right? Which we're not dealing with. So we're dealing with the limit as m goes to infinity. This whole thing. Well, this last part is really, I mean, it's just 8 divided by 1 is 8. We've got a minus and a minus, so that's just going to be plus 8. Now let's decide what happens here. As m becomes really large, this is going to look like negative 8 over infinity, if you were to think of it. This is, so when in a denominator of a fraction, when it gets really big, it causes the number to become really small, to actually go to 0. So the limit of this, as m goes to infinity, this part is equal to 0. So we get 0 plus 8, which is just 8. So we would say this one converges, and that the limit is 8 and converges, and it converges to 8. Okay. So that's how we're going to do each of these. We'll move on to the next one. Again, it's all, we tried, there's not even a way to really, I mean, you can graph these just to kind of see if as you get larger, as x gets closer to infinity, if it's sort of filling in the gap there. But there's not necessarily a good way to tell. So again, we integrate this part, and we want to think of this as involving a limit. M goes to infinity. It's not really important to call it M, but since that's what the textbook is, I'll just stick with it, right? We replace the infinity by this M, which is some finite amount, a limited amount. It doesn't go to infinity. And then we use limits to make it go to infinity. To integrate e, an exponential, remember we get the exponential back, e to the minus 2x. And then with the shortcut rule, we have to divide. So this is just a constant times the x, so we divide by that constant, minus 2. That's how that's going to integrate. The integration, the limits of integration, we go from 4 to m, and again, we still have our limit as m goes to infinity. We're now going to plug in our limits of integration. That's according to the fundamental theorem of calculus. And again, we've taken the review in a little different order than we learned things. We actually learned this, I think, 14.1 or 2, or so we'll get back to it. I think it's 14.2. So anyway, we plug in the limits, so we get, or not the limits, the, well, I guess these the boundaries of the integration. So I put the m in for x, so I get e to the minus 2m over negative 2. Now, since it's got a negative exponent, I could also put this in the denominator, which I think I'll do in the next step just to make it clear exactly what's happening. And then we subtract the function with the lower limit put in there. E to the minus 2 times 4 over negative 2. Now this limit, as this goes to infinity, since it's a negative exponent, it's really, we want to think of this as 1 over, look at the negative out here, 2e to the 2m. As m gets big, e 2 times m gets really big, e gets really big, so the whole denominator gets really big. This whole part goes to 0. Okay, so this goes to 0 as an m goes to infinity, this is going to go to 0. This part over here, it's all numbers, so it's going to go 4 times 2 is 8. So let's go ahead and rewrite that. We've got a negative and negative, so that becomes a positive. So this becomes 1 over 2e to the 8. And with the 0, so that is our answer. So we can, again, we can say this one converges to 1 over 2e to the 8. And I haven't checked the answers on these. I'll go back and do that just to make sure, so you can be assured that I didn't make any mistakes along here. If you catch them, that's good, so I'll leave them, but I'll do a follow-up at the end of any potential errors. But I want you to see, I want you to learn more how to think through these and go through these, and then to try to spot how any errors. And I'm trying to do that as I go, so hopefully you're finding these helpful. Okay, let's just move this down to the next page. Makes it a little easier. Okay, so again, the first thing we do here is we rewrite the integral, the limit as m goes to infinity. We replace the infinity with a finite amount, which is a non-infinite amount, right? I'm going to leave this as 1 over x. You could write it x to the minus 1, but when I see this 1 over x, it reminds me this is different than adding 1 to the exponent. This is natural log. This is going to integrate as natural log. Now, if you remember that x to the minus 1, if you remember this integrates to natural log, you're more than welcome to go ahead and write it this way. Okay, we've got to choose a way. I'll do it this way, but I'll comment you can do it that way. Okay, so this becomes natural log. Okay, so we're going to integrate. 1 over x integrates as natural log of x. Natural log of x. That's it. That's it. That's it. I was trying to do too much at once. The limits of integration going 1 to m. And again, we're taking the limit as m goes to infinity. Okay, so now we put in our limits. So we put the upper limit in first. So this is the natural log of m, the limit of m going to infinity. The second part, since we're plugging in a number, we could think that the limit applies, but it doesn't really matter. Limit of 1. Now, limit of 1 is a number. I believe it's 0. Yes. However, the problem we get here is when m goes to infinity, natural log of m also goes to infinity. It gets big slowly, but it gets big. So this one, this part, diverges. Now, how do I know that? Well, you have to look at those rules we looked up and remember what converges and diverges. So this goes back to chapter 1. But another way you could do that is we can take a look at what happens to the natural log of x. Natural log of x as we graph it. So we see it going up, and so this is our limit. As our limit goes up, this is going up. And again, what you want to do is make your window. See, we're only going out to 16. Let's go out to 1,000 in the x direction, and you'll start to see it keeps going up. It does. It goes up slowly. This is out at 1,000. It's not too high, but it's going up. It's going to continue to add significant amounts. Okay, and again, if you want to see that again, let's go to 10,000. Oh, let's go to 100,000. Okay, it keeps adding. It keeps adding. It's not going to converge to something. Okay, so again, sometimes the graphing calculator can help us to see what converges and what diverges. So let's come back to this one. And we're going to take the limit as m goes to infinity. And we're going to rewrite this going from 3 to m. X squared dx. So we'll just kind of continue here with this x squared. We just have to add 1 to the exponent. So 1 plus, or 2 plus 1, 1 plus 2, either way, gives us a 3. Remember, we always divide by the new exponent, because if you take the derivative, the 3 comes down, so that's going to cancel. And then we have our limits of integration. We're going to go from 3 to m, and remember, we still have our limit out here as m goes to infinity. You might think, well, I'll just remember that it's a notational thing. Okay, we plug in our limits of integration. The top one goes first. So this becomes m to the third over 3 minus the bottom one plugged in, 3 to the third over 3. And we take the limit as m goes to infinity. Now, if this last one diverged, the natural log, and it's a slow rising function, x cubed, as we know, just shoots off to infinity pretty quickly. Either way, both of them go off to infinity, so this part diverges. And again, you could graph this and you would see a graph of a cubed, x cubed over 3. It has this little loop-de-loop thing here, sort of, and then goes off. But it's this part, here's m going off to infinity. As this goes off to infinity, that's going off to infinity as well. It's actually infinity cubed, but however you want to think about it, it's definitely not going to converge. It's not coming back down. So it really doesn't matter what this is. If basically think of infinity minus something is still infinity. This would be 20, so this would be 9, but it doesn't matter. It diverges. Okay, because of this part. And we come to this part. I'll also make up a little resource that has some of those shortcut rules. Look over your limits as well. There's some of those shortcut rules for limits that you could look and say, oh, this type of a function, 1 over x, that's going to converge. X to any power is going to diverge, those kind of things. Now here is one with the infinity is that it's going to negative infinity. It's a lower limit. We treat it really the same way, except remember, this is negative when we're plugging it in. It's anyway, we'll see how it works. It's going to negative infinity. So we write the limit with m going m to 0, but this time it's the limit as m goes to negative infinity. E to the 2x dx. When we integrate this part here, it just becomes e to the 2x, and remember the shortcut rule says we have to divide by this constant in the coefficient, right? So we divide by 2. Our limits m to 0, and we still have our limit here as m goes to negative infinity. So when we plug in our limits, we plug in the top one first again, so this becomes the limit as m goes to infinity, e to the 2 times 0 over 2 minus e to the 2m over 2. Go like that. Now, 2 times 0 is 0, e to the 0 is 1, so this front part, this front term, simply becomes 1/2. What does this back part become? Well, oops, I forgot the little negative, right? We're going to negative infinity, so this is becoming a more and more negative number, so this is going to act, because we're going to the negative side, as 1 over 2 e to the minus 2. So I bring the negative side out there times infinity. 2 times infinity is a very large number. It's a very large, well, sorry. Since I moved it down, let me do the steps. This is like e to the minus 2m over 2. Move it down, it'll become like this. It's going to become very large, right? E to in an infinite power. It's very large. multiply by 2, but it's in a denominator, so it's very large down here. So this part goes to 0. The limit takes it to 0. So this is 1/2 minus 0. So it converges. To 1/2. Okay, and those are all the ones we have. And again, had it been going, say, from 0 to infinity, that would diverge, right? Because we wouldn't have had this negative. It would have been up here. This goes off to infinity. It diverges. But because it was the lower limit and it was going to a negative infinity, that negative got incorporated here, moves it down into the denominator, and that's the whole difference. So one of our, the rules are basically, 1 over infinity, this will go to 0, but infinity over 1, that goes to infinity. Okay, that diverges. That's what we call diverging is going to infinity. Converging is going to a particular value. And again, a lot of times it's 0 that it goes to. So those are our practice problems for improper integrals. I will get to work on the last series of 3 sections dealing with area between 2 curves. And then we'll be ready to just kind of keep moving forward and get ready for that last test. Thanks.